Hello, welcome back to Math 480. The four things we'll be doing today are listed. First, if you've graded somebody else's homework, make sure to hand it in right here so that Robert Miller can grade it. So if you haven't done so already, make sure you hand it in. Second, we're going to discuss the projects and also just the general schedule for the class for the next coming 2 weeks. And by discuss projects, I mean we'll discuss how they're going to be graded and presented and so on. Finally, after that, I will talk for a few minutes about scipy.stats, which is the kind of native Python stats functionality that's in Sage. And finally, for the last 20 minutes, we'll do evaluations. So this is a very easy pop test, which Allison will be administering. So, and I want to be absolutely certain that I don't not give you 20 minutes to do. Is 20 minutes normal for evaluations here? What is the normal amount of time, actually?
It's like 4 minutes, and you don't have that time. But
no, but what are you supposed to do? Seriously, 15 minutes. Okay. So,
a bit long.
okay, so I'll make absolutely certain that at 2:05, definitely we'll do evaluations. So I don't want to shortchange you, since I really do value your feedback. So at 2:05, the alarm will go off. Okay, so that's what we'll be doing today. So again, reminder, hand in the graded homework here. So now we're going to talk about projects. The first thing is that, a reminder, the final project counts as 40% of your grade. So it's a significant part of your grade. There's no final exam again. I guess, in the first week of June, when we finish doing final projects and when you turn them in, you're done with this course. You don't have to do any final exam or anything like that. And also the final project, as listed here, it's due before final exams, Friday, June 6th. So you won't be worried about this course at all while you're studying for taking your other final exams. In order to help organize the projects, so everybody's going to have a chance, or at least every project will have a chance to present their project for about 7 minutes. And in order to organize that, I need you to, on this piece of paper, put a brief description of your project and the people who are involved. Okay? And I will post this list on the wiki and then send out an email to make sure everybody gets on it. But maybe Allison can start. And I guess I could leave my pencil too, in case I can send that pencil around with it. So just put your project, just some sort of brief description of your project. The main point of the description is I'm going to make a schedule for the project presentations, and I want to group similar projects together. So if your project's on graph theory, put something that is just enough to indicate that graphs are relevant and the people. So that, if you put some like technical thing that I have no idea what it has to do with, that'll be difficult to decode. So put sort of a category-ish description and a couple of words there. By the way, when your project's finished, it'll get posted on this wiki at the end of the course. So you don't want to do a bad job because it'll get posted. The way the actual schedule will work is that I've changed the schedule slightly. If you go to the Sage schedule page here, sorry about my net connection. So what we're going to do today is talk a little bit about scipy.stats. On Monday, you'll enjoy your vacation. On Wednesday, we'll talk about scipy.stats in more detail and R. And on Friday, we'll talk about R. Then the entire last week is going to be presentations. And then there'll be a schedule for this. Each one will be strictly limited to 7 minutes so that everything will fit. And one key thing about the presentations that I'll explain in a minute is that they will matter for your grade. So there are a lot of details here, but as you can see, if we have 3 days to do presentations, then that's 150 minutes. Because some people are doing projects together, I estimate there are roughly 20 projects, so it's about 7 minutes per project. So you want to be very well prepared if you're going to present something in 7 minutes. You want to practice, for example. By register, all I mean is write something down on that piece of paper that's going around, and I'll confirm it via email. And I'll draw up the schedule, which I'll tell you about next Wednesday, so you'll know what day you're going to present. Now the grade, it's, in the past I've always graded final projects for courses by basically looking at it myself, looking at the student saying something and then just coming up with a grade based on some like, haphazard guess. And I'm going to try to, well first you're used to grading each other a bit on the homework, so a tiny fraction of your final project grade will be determined by what other students think of your final project. Okay? So what will happen is that when you watch other people give their final presentations, which will be, again, during the last week, you'll decide on a scale of 1 to 3 how good you think it is. And the sort of criterion I hope you use are listed here, like the presentation, the overall quality, how interesting it is, whether the person just finished or not, etc. And, but you don't have, I mean, you can use whatever criterion you want. So if you come up with a project that's completely incomprehensible to anybody in the class, except maybe me, then that might hurt you. Or if your presentation is just absolutely terrible because you didn't put any time into it, that might hurt your score. But it's not very much of your score. Also, I will certainly look at the student scores. So for example, what I'll do is I'll just take all the scores for a given project that you give on your piece of paper and average them. And if they're completely out of whack, or if there's a bunch of students said that somebody's project's terrible and I thought it was great, I reserve the right to just adjust any of the student scores up. So, but this will give you a chance to kind of think about what you're seeing and put into writing how good you think some of the presentations are as well. Also, there will be a little bit of effect on your final project grade from the TA, who will also assign a grade to every single project in the same way I will, and his score will count for 20%. And then I'll have the remaining 60%. So it's not just me, although I reserve the right to revise grades up that the other people give. Okay, any questions about that? I mean, basically, you get a little bit of say, just a little tiny speck. I guess you get about 1/600th of a say or something on everybody else's final project score. Not too much, but it's something. And these are some of the criterion that I will use in grading your final project. So first, the 7 minutes when you talk. Not every person will talk necessarily, but each project will have somebody speak for it. And that will count for some amount of the grade. The overall quality. So for example, if you write a bunch of code and it's just terribly written, there isn't a single comment there, it's halfway broken, that's bad quality. On the other hand, if you just, good, you know what good quality code is versus bad quality. And the same with writing. If you do something that's interesting, that's definitely a big plus. It's really, really boring, that's not a plus. If you try to do something and you decide to do X and you do, I don't know, square root of X, then that's not necessarily so good. If you do something and it's, say, no shape for anyone to use really, but it's a really cool prototype of an idea, I think that's perfectly fine. That could be a perfect grade. So for example, your chat thing, it's kind of a mess if you wanted to put it into Sage, but it's a really cool prototype of something that's really neat to try out. And, or maybe you do a worksheet that computes something involving prime numbers, I don't know, and it's really not something that's all suitable to ship to other people, but it's a really neat illustration of some idea, then I think that's perfectly fine. You shouldn't worry about that at all. And if you're really unsure whether your project is at all this, I mean, you really wonder, should you be doing this or that, if you want to get a reasonable grade, you should ask. You have plenty of time to ask. And hopefully very available to be asked. So that's the projects. I'll just leave that there for a second and see if you have any questions. Yes?
So for what we actually submit, do you want, like, say to submit a patch for the code we wrote and then maybe some sort of write-up?
It's going to depend a lot on what you're doing, but in a lot of cases you can imagine writing roughly a page, one single page that describes what the heck you're doing. It depends a lot. I mean, there's a really wide range of projects, but I think in a lot of cases it would be useful to have one page that describes what you're doing plus something else. I mean, it really varies a lot based on the project. But for example, one person is refereeing some code for symbolic logic that implements a certain algorithm. And part of their thing they hand in will be a page that describes that algorithm. And then the rest will be just some remarks about the code that came out of them reading it. Another person's implementing an algorithm for doing something involving network flow. So it would be really good to describe that algorithm in about a page, plus the relevant code. So I think it depends a lot on the project, but if you're worried or don't see how, it's really unclear to you what your deliverable should be, you really get to decide what you're going to give me. But if it's really unclear to you what you can possibly give me given what you're doing, just ask me. Like, what are you doing?
I was going to implement some visualizations of group theory, so I guess I'd probably submit some code.
Yeah, but you might want to write a page just describing what group theory you're visualizing and possibly include like a couple of screenshots or something. So it's easy for somebody to look at it for a minute or two and just get a sense of what's going on. Okay, so, I mean, imagine if there were a little page on the wiki devoted to your project, what might you put there? So, but again, there's no hard and fast rules about what you turn in. It could vary a lot from person to person. And again, as you've noticed from the grading, a big part of what you're going to do is just present what you've done. So for you, that could very well be just showing some of these visualizations to everybody in front of the group. So that will be a substantial part of what will determine your grades. Just, can you show some nice pictures and maybe give a few examples? So regarding the actual presentations, I'll have my laptop connected with the projector, and it will be online, and you'll be able to, show some slides or run some code in Sage or whatever. And you could try to connect to your laptop, but that will cut into your time possibly. So it's a risk. Okay, other questions? I'm going to wait 20 seconds to see if you have any questions, just in case.
To make
Yes?
transfers smoother, can we send you a worksheet? And
Transfers of what?
So people's presentations can go smooth.
Oh yeah, yeah.
And send you a worksheet.
Absolutely, and I'll have it already on my computer, yes. Yeah. Yeah, for a lot of, not everyone, but certainly a number of people, it'll be a worksheet's best. I think with your chat program, you'll probably just want to plug a laptop in because it might be so tricky to get it set up just right. Or you might just work on the same network, so.
Yeah, I think we might have it where we could just have people log into it.
Yeah, that could be fun. Okay, so other questions? Okay. All right, so now on to statistics. Sage has some statistics functionality, and that's what we're going to be talking about for the rest of this course. The statistics capabilities in Sage are in two completely separate pieces of code. One is SciPy, and a little bit of NumPy. I showed you just a tiny bit of this last week. For example, NumPy, you can do things like make a NumPy array and ask for the correlation coefficient matrix. So you can compute statistical properties of NumPy arrays. So that's something related to stats that involves NumPy. And then SciPy has something called SciPy.stats. And that's mainly what I'll talk about today. SciPy.stats is a very systematic organization of 80 continuous distributions, 80 continuous probability distributions, and 10 discrete probability distributions. Where each of these probability distributions, or random variables, has various parameters that describe its shape. So there's a lot of different things in here, and there's various pros and cons. But then so this is kind of the one part of statistics in Sage. Then there's another separate aspect to statistics in Sage, which is that R, which is one of the most popular programs for doing statistical computing, is also included in Sage. And there are two interfaces between R and Python, which Sage includes. So I'll be talking about that more next week. So you have R, and you have SciPy.stats, and NumPy. I think, it would be much nicer in a sense if statistics in Sage were something that weren't just this or that, but were maybe something that very nicely builds on top of them and gives you some beautiful, wonderful, coherent presentation of statistics. That doesn't exist. Maybe it will in the future. I hope so. And there are various issues with SciPy and NumPy stats. There are issues with using R, etc. So all kinds of issues. But the fact of the matter is, if you want to do statistical type stuff, and you're just at work trying to do it, Sage does work pretty well, and you can get work done. Like in my research, I often have to consider using statistical methods or drawing random numbers from some sort of distribution or whatever. And SciPy.stats actually works extremely well for that sort of thing. So at the end of the day, it does work really well. But it could be better. Definitely could be better. So first, here's the web page for SciPy.stats. And let me zoom in a little. So SciPy.stats is a module. It provides tools for statistical analysis. And as I mentioned before, there are 80 continuous distributions and 10 discrete distributions. And for each of these, there are a bunch of functions related to them. And then there's other things. So this is just an example, I think. So there are 2 PDF files that describe precisely the continuous and discrete distributions that are included in SciPy.stats. Before doing that, let me just do a little tab completion magic. If you type import SciPy.stats, SciPy.stats.tab, you will see that there are a lot of different functions here. In fact, you can't even see them all. They're going for pages and pages. So somebody had a lot of time on their hands, and they sat there and implemented a lot of different functions, as you can see. That somebody, I think, being mainly Travis Oliphant, who's the main author of NumPy. And actually, before diving more into using this, let me show you where the source code is. So if you take a copy of Sage that you've downloaded from source and go into the spackage standard directory, there's a file scipy and then a date.spackage. If you extract that file using the tar command, which I think OS 10 would do that automatically when you double click on it, then you'll see a bunch of files fly by. And if you go into the resulting directory and into the src for source directory and then scipy and then stats, oops, you'll find the source code for the scipy stats module. And here it is. It's almost all pure Python. A lot of it, I think, well, some of it builds on top of other things, of course, that are compiled, but it's under 10,000 lines of pure Python code. So it's not too long. If you want to understand how something in scipy stats works, you can probably just look at the source code and get some useful information out of that. And just to take a glance. Oh, hey, I take back what I said. It's not just Travis. So for example, there's lots of people who have copyright and this sort of thing. So Gary Strangman, whoever that is. Let's see. I guess the biggest file by far is this distributions file. This is written by Travis Oliphant. So this is where these 80 continuous and 10 discrete probability distributions are defined. So there's lots and lots of these. Okay, so that's the source code. And there are these 2 documents, continuous distributions and discrete distributions, that describe the distributions that are in there. And here's an example of one of them. Here's the so what happens is for almost every distribution you have a bunch of these functions defined on them, which give you additional information about that distribution. By the way, some people probably don't know any stats at all. And, when I say distribution, you can just think of a function f of x with the property that when you look at its graph and integrate it from -infinity to infinity, it's also non-negative. And when you integrate it from -infinity to infinity, you get 1. And you can think of this plot as giving the probability that if you choose something randomly, it will lie in some little interval. So for example, the probability that something will lie in this interval, that's the integral from here to here. So the probability that a randomly chosen value lies somewhere is 100%. That's why that interval is 1. So that's kind of so distribution in the sense of what we're talking about here is simply a continuous function from minus infinity to infinity with the property that this integral exists and is equal to 1. And there are a lot of distributions that come up in statistics, like, for example, a uniform distribution from -1 to 1. Another very, very popular distribution is the normal or Gaussian distribution, which of course comes up in all kinds of different natural contexts. And that's the famous bell curve, which I haven't drawn very well. It's just one of the many distributions you have here. And then given a distribution, there are all kinds of different things you can associate to it. One thing is the cumulative distribution function, which is integral from minus infinity to some point. So that counts the probability of something being less than or equal to a given value. And so given a probability distribution, there might be a nice simple closed form formula for the cumulative distribution function. That is an antiderivative of this f. And so that's the sort of thing you want to record. So you'll find big, big tables of these sorts of things in various locations. And that's really basically that sort of stuff that's encoded in scipy.stats. It's nice that you systematically have a ton of different distributions here. So I'm just flipping through the pages, but there's a lot of distributions that people have considered. Not every single thing is normally distributed. And very often, distributions, like the normal distribution, there are two parameters that define it. One is the mean, and the other is the standard deviation. So if you give those two numbers, the mean and the standard deviation, then there's this nice curve that's associated to it. And in all of these cases, these distributions are determined by some parameters. So I have no idea what the Nakagama distribution is, except, well, there it is. It's defined by the parameter nu, and it's given, there's the function f, and presumably if you integrate that, I guess, from 0 to infinity, you'll get 1. And then these are other things attached to that distribution. There's the normal distribution. I wonder, it doesn't seem like it's in order. So what does Maxwell come after normal? But there you see it. It's e to the minus x squared over 2. That's where it doesn't seem to have the standard deviation or the mean as parameters in the description here for some reason. Okay, so let me show you some of these in action. So here's an example of a distribution, the semicircular distribution. So this is something that, or this is something that comes up a lot in the study of elliptic curves, as it turns out. Actually, I'll tell you the biggest theorem about elliptic curves in the last, 6 years. It's a major, major theorem. So an elliptic curve is a cubic curve of this form where the a and b are integers, and the cubic on the right-hand side has distinct roots. Now here's a little game you can play. Take this cubic curve, and for each prime number p, since you're a number theorist, you're like prime numbers, what you do is you count the cardinality of the set of pairs x comma y, both integers, between 0 and p minus 1, such that the following congruent, so it's y squared, or even less, I won't say congruent, such that p divides the difference y squared minus x cubed plus ax plus b. Okay, so that's an integer. For each prime number p, you can just count up how many solutions there are to this equation mod p. Or what's the same is ask how often p divides this difference. You could do it easily because there's only p squared possibilities to consider. You just check each one to see whether it divides or not. In other words, you're looking for solutions to that equation but modulo the prime p. And if you just let these be n sub p, it turns out that they're very close to p. Because if you know a bit of number theory, as you run through possibilities for x here, there's roughly a 50-50 chance that you're going to get a perfect square here, modulo p. And once you do get a perfect square modulo p, you can switch the sign of y, and you'll get the two possibilities. So there's roughly p solutions. So what's interesting to do is to measure the difference p minus np. That's the difference between p and np. And you call that a sub p. And it turns out it's at most 2 square root of p. Well, I'll just leave it like this. So just call a sub p this difference. And now it's a theorem that ap has absolute value less than 2 square root of p. So if you take for each prime number p and compute the number ap divided by 2 square root of p, which I will call bp, then you get a number that's between -1 and 1. It's in this interval. Now it turns out if you graph these numbers and kind of make a frequency histogram, so you just decide to divide up the interval from -1 to 1 into 100 equally spaced chunks. And now for thousands and thousands and thousands of primes, you compute n sub p, you count the number of solutions this has, modulo p, you get all these numbers, you divide them up into a little histogram. It turns out that what you get looks like a semicircle. It doesn't look normal at all. It looks like a semicircle. And that's a theorem, in fact, that these things, these numbers bp, if you keep using more and more primes and then drawing a histogram, the result will look like a semicircle. It's called the Sato-Tate conjecture, which Richard Taylor has proved in most cases recently. The Sato-Tate conjecture says the bp are distributed like a circle. Like that. It looks like a semicircle. And so, of course, you're interested in maybe the semicircle distribution, which is an example of a distribution. Just the function. You just take the graph of the semicircle, normalize it so that the integral under the semicircle is 1, and that gives you a probability distribution. And then you can start sampling from it. You can ask to compute its cumulative probability density function and so on. And so we can try that in SciPy. Actually, just as a quick challenge, let me convince you that that's true by taking an example elliptic curve, completely, say, at random. We'll make the a and b be 3 and, well, actually, I'll let you make it up. Somebody choose an a and a b. Quick, because I don't have much time.
2 and 5.
2 and 5, okay. 2 and 5. There's the elliptic curve, okay, just like that. Got it. So I'll compute the BP. There E dot AP. There's a function to compute AP divided by 2 times square root of P. So P in prime range will go up to, say, 100,000. So it's now computed all of those numbers BP. Now let's divide them up into, let's make a histogram that counts how often they fit in each little interval. So SciPy has a nice histogram function, SciPy.histogram. And if you just give it as input any list of numbers and how many bins you want to have, let's say, I don't know, 50, then it returns the counts for each bin and the x, the left endpoints of each interval. And so if we just take, say it's bar chart, if we draw a bar chart with these bins, there we are, just like that. So notice that looks a lot like the plot of a semicircle. You might not be completely convinced, but if you draw the same thing, say for 1 million, which should only take about 10 seconds, and then maybe take 100 intervals, it's going to look even more like a semicircle. There it is. And by the way, proving this is something that stumped people for decades and decades. But it was recently proved only about a year or 2 ago. So it does look like a semicircle. So now let's use SciPy. In SciPy, one of the many, many continuous distributions, one of the 80, is semicircular. And what this does, there's a whole bunch of functions on it. So I do a.tab. Here are the different functions. There's this CDF, which gives you the integral from the start to any point, quite efficiently. And there's other functions, like stats, etc., that tell you about the semicircle distribution. And one of them is RVS. Let me try that out in a simple case. This computes n random samples, assuming that you have that distribution. So what this does is it's choosing numbers at random in such a way that if you were to plot the frequency histogram, you would get a semicircular distribution. Okay, so you can imagine that could be a useful thing to have at your disposal. If you want to do some sort of Monte Carlo experiment where you generate random numbers and then do this over and over again and see how that compares to some clever idea you have or strategy you have for a game or something, it's nice to be able to draw random numbers and not have them just be uniformly distributed. So you can tell it'd be incredibly useful. And moreover, it would be very, very good if this were blazingly fast. I personally find it incredibly useful if this were blazingly quick. So let's try it for 5,000. This should give us 5,000 of these numbers, and then we'll draw a bar chart. And disturbingly, this actually is taking a lot longer than it took us to compute the number of solutions to that cubic equation mod, all the primes up to 1 million, which is there are a lot more than 5,000 primes up to 1 million. So it's kind of annoying. Why didn't it print out the time? Oh no, I hit refresh. Okay, there we are. So it took 10 seconds just to do 5,000 samples, which I find very lame. But look, it does look like a semicircle. So this is the data that came out of SciPy by calling the random variable sample function repeatedly on the semicircle distribution. And you could do this with any distribution in SciPy, any of those 80 continuous distributions or whatever. You just create the distribution, then you call RVS with some input number, and it gives you back that many randomly chosen values. Using an algorithm that chooses the values in such a way that if you draw the histogram, you'll get something that looks like like the distribution function. Okay. But it's actually extremely disturbing to me that it takes this long it takes over 10 seconds just to choose 5,000 random values that are distributed like this. And I think that is terrible. In fact, playing around yesterday, I wrote this little tiny stupid function, not thinking that hard, which should do exactly the same thing. What it does is it says, if you choose variables uniformly at random and then plug them into this function, which uses numerical root finding, which is kind of ridiculous to invert something else that I computed symbolically by symbolic integration, then these numbers will also be distributed in a semicircle distribution. So every single time I evaluate G, it's literally calling some numerical root finder. And yet it's still almost 100 times faster than SciPy's function for doing the same thing. And just to convince you that I haven't completely messed up, if you look at the histogram, it does look like a semicircle still. So I was really curious about why it's so slow. I looked at SciPy's stats module, and that's why it's all written in here. So semicircular is in here. So there it is. So what he has is a couple of formulas that define special things, and this derives from some generic framework, which, given just this information, it can do everything else that you want, like sample random variables and so on. But it's implemented in such a way that it's pure Python, and I don't think it's optimized very well. There's literally, when you profile doing that one calculation, there's several 100,000 calls to various Python functions and stuff. So I don't know, it's just really, really slow and annoying, because I'd really like that all these distributions are fast. I mean, the usability is really good, but the speed is, it's really terrible that it takes, that long. It's just ridiculous. It's just a sample of 5,000 values taking 10, 11 seconds. So I searched around the R documentation to figure out how to do the same thing in R, but I was unable to. Me and some other people were unable to figure out how to do this in R within 15 minutes. So I will have to try to figure out how to do that next week to see if R can do this sort of thing very, very quickly. But somehow, one way or the other, I would very much like I mean, I really like the interface to using SciPy stats. It's really nice, clean, simple, easy to use, very Pythonic, very nice, but it's way, way too slow to be, I think, good enough for really serious work, which, at least in some cases. Okay, so these are some examples of other SciPy functions. Now, as promised, I will stop. Fortunately, I'm at the end of the summary. A lot of work needs to be done still on making stats way better in Sage. However, if you just want to do something right now, there is a lot of power there. Okay, so I'm going to kind of close up shop, and then Ali's going to hand out the handouts so you can evaluate this course. And hopefully you don't evaluate it too badly, because I want to turn this into a course that's offered every year, taught by various people. So these evaluations will probably matter for making a case to turn it into a course. I think also the sorts of things you write will matter too. So if you have ideas that would be relevant to this being turned into a normal course, kind of like the applied maths in the 300A MATLAB courses, then please do write those down.